Alright, good afternoon everyone. Welcome to the third lecture of matching theory. Eventually I lose track of which number of the number of the lecture. Okay, so today we'll keep it light. We won't prove a major theorem today. We will do some more sort of basic things in some sense. And we will focus mostly on examples, right? So we know what a matching chord graph is. Let's just connected at least one edge, and each edge is matchable, which in turn means that it belongs to some perfect matching. Okay. And if it is the first time you are studying matching chord graphs, then it may seem like this is a very restrictive class, such a strong condition, right? Okay, connected and at least one edge is fine, but every edge belongs to some perfect matching. Right? One may think, many times when I give a talk, people are like, oh, maybe there's only a small set of graphs that have this property. Right? So, well, that is very, very false in a sense. So let's look at some classes of matching chord graphs. And since we are going to discuss classes, we will also discuss operations, because many classes are defined using operations. Okay, and the content we are covering today is basically some of the more basic topics from chapters 2 and 3. Of Lucchesi Murthy 24. Okay, so one of them you already know from SGT assignment 5, problem number 5. Every two connected cubic graph is matching covered. Right? So SGT assignment 5. In the lectures we prove that every two connected cubic graph has a perfect matching, is matchable, and in the assignment you prove every two connected cubic, by cubic I mean 3 regular, each vertex has degree 3. Graph is matching covered, and the easiest way to prove this, so this was originally proved by Schönberger, (1934), and earlier Tutte had proved weaker statement is matchable, not Tutte, sorry, Petersen. This was proved earlier by Petersen in 1891. However, today almost nobody would prove it the way they proved things, because we have more technology called Tutte's theorem. Right? So the easiest way to prove this statement is to use Tutte's theorem. So first you use Tutte's theorem to show that this graph is matchable. Then you basically prove that every barrier is stable. Therefore it is matching covered. Right? That is sort of the easiest way to do it, and that is actually how we do it on this structural graph theory course. Right? Okay, so that is a large class. We all agree? Two connected cubic graphs. So everybody agrees that is a large class. Right? We are just insisting that every vertex has degree 3 and connectivity is at least 2. So there are no cut vertices. Yeah? Okay. So that is a large class of matching chord graphs. Okay. Good. For example, there's a famous class called snarks. Snarks are two connected three regular graphs that are not three-edge colorable. Snarks, there's a lot of literature on snarks. We literally went to a whole workshop in Paderborn on snarks, where 22 people all over the world came over to discuss snarks for how many days? Maybe 3 days? 4 days, yeah. So, well, snarks is a large class and that is a subset of two connected cubic graphs. Right? Okay, good. So what else? So that's one. Now let's talk about another problem from SGT assignment 5. Where you prove an Hetyei decomposition theorem for bipartite matching covered graphs. But well, before we go to that, let us observe, well, I will give it as a DIY of course, very easy. Every matching covered graph is two connected. There is one exception. What is the exception? K2. Standard exception. So, DIY yeah, every matching covered graph except K2 is two connected. Okay, and in particular, every matching covered graph, including K2, is non-separable. Yeah, and for non-separable, almost the same as two connected in this context, we know that there is an Hetyei decomposition theorem by Whitney, 1932. So when you see non-separable or two connected, you immediately think of Whitney 1932 Hetyei decomposition. So it turns out, well, so of course, for any matching covered graph, you can construct an Hetyei decomposition, right? Depending on how you define Hetyei decomposition, you may include K2 or you may exclude K2. So either you can start the Hetyei decomposition from a cycle, which is what I typically do in SGT. So then of course you have to exclude K2. But you can also start Hetyei decomposition from K2, add an year, get a cycle, continue. Right? So, technicalities. So of course for any matching covered graph, you can construct an Hetyei decomposition. So that means in any matching covered graph, except for K2 or cycles, depending on your favorite, you can remove any year and get a smaller two connected graph. Yeah, because it is a two connected graph, you can just apply Whitney's theorem. But that's not very interesting. What would be very interesting in this context is if you could remove an year or some type of an year so that you get a smaller matching covered graph. And that turns out to be true in a very, very literal sense for bipartite matching covered graphs. So, bipartite matching covered graphs admit a special type of Hetyei decomposition. Yeah, and this special type, I will explain what this is. Basically, it should preserve the matching covered property. At each step. Right? If you can do that, that could potentially be a very good induction tool because you are able to preserve the matching covered property at every step. Yeah? Okay. And that is exactly what Hetyei did in 1965. If I remember the year correctly, Hetyei 1965 proved this special type of ear decomposition theorem. So we'll just do an example and see what this looks like through an example. Supposing I want to construct the cube graph. You can all check that this is a bipartite matching code graph. Well, in particular, this is a two-connected cubic graph. Therefore, it is matching covered. Right? So here is a very nice bipartite matching code graph. And let's see if we can do what Hetyei said. So Hetyei said that you can start from an even cycle. So let's actually try an interesting example. Supposing I start from this cycle. Now I want to add, cycle is matching code, yeah? The cycle is matching code, of course. It's even cycle. It's a matching code graph. Now can I add an year to get another matching code graph that is a subgraph of the given original graph, the cube? Do you see any way of adding an year to get a bipartite matching covered graph that is a super graph of the pink graph but a subgraph of the whole white graph?
It should be two connected as well, isn't it? Just matching cover.
Well, every matching code graph is two connected, so it will be two connected because it won't be K2 anyways. So can we do it from this cycle? Do you see any way of adding an year? No, right?
No.
You don't see any way of adding an year. In particular, observe that every year you can add is a path of even length. A path of even length will change the parity of the order of the graph. So it won't be matching code for sure. Right? You need an even number of vertices. So the issue with this cycle is something we'll come to. Okay, let's start with some other cycle. I'll redraw the same graph. So this cycle does not work. We are not able to get a bigger bipartite matching code graph by adding an year. Let's do another cycle. I will again take a 6 cycle. This was also 6 cycle. Now I will take another 6 cycle. I should color the vertices. Now can you add any year? Let's label the vertices. 0, 1, 2, 3, 4, 5, 6, 7. Now can somebody tell me what is an year to add? Give me a long year, not a single edge, to make it more interesting.
5, 1, 2, 6.
5, 1, 2, 6. Great. Let's add this year. 5, 1, 2, 6. Observe that this is again a matching covered graph. And of course it is bipartite because the original graph is bipartite. Great. And now this is not the whole graph yet. So let's add more years until we complete the whole graph if we can. So can we add another year now? Somebody else? 0, 1. Okay, we can add 0, 1, single edge here. And then we can add another single edge here. We can add another single edge here in that sequence or any sequence. Now observe that at every step you have a matching covered graph. The original pink graph is matching covered, pink union blue is matching covered, and pink union blue union any subset of the yellow edges is also matching covered. Yeah? Right? Alright, so this is what Hetyei said. Hetyei basically proved that for any bipartite matching code graph, you can come up with an ear decomposition such that every graph in the sequence is also matching covered. Right? So let's say HAB is a bipartite matching covered graph. So I'll write one direction for now. Then what Hetyei's result says, there exists a sequence of matching covered subgraphs H0, H1 up to HR. These are subgraphs of H, such that the first graph, up to you, you can take it to be a K2 or you can take it to be an even cycle. In SGT I use even cycle, so maybe I'll stick to even cycle. But I think Look and see Murthy allow K2. Okay, so maybe I'll say, for now I'll say except K2. But it really doesn't matter. Such that H0 is an even cycle. Well, it has to be even. My graph is bipartite. HR, the last graph, is the graph you want, as usual in an ER decomposition theorem. And what is really important is that every subsequent graph, every graph in the sequence is obtained from the preceding graph in the sequence by adding what we will call a single ear. And by a single ear I mean a path of odd length. And the reason for single will become clear eventually, right, when we go to non-bipartite graphs. And Hi plus 1 is obtained from Hi by adding a single ear, and by this we mean path of odd length. Which naturally means it has to join a black vertex to a white vertex. It's a path of odd length in a bipartite graph, so therefore it will join two vertices of the opposite colors. Right?
This restriction is not there. We can add path of even length as well. Ear of even length as well.
In which?
In ear decomposition.
In general, yeah. In Whitney's ear decomposition, you can add any path of any length, so long as you get a two connected graph, which you will always get. If you add an ear, you will get a two connected graph. Exactly. Yeah. If the original graph was two connected. Yeah. Here we are only allowing adding a path of odd length, and the addition should give us again a matching covered graph. That is what the theorem is saying. Yeah. So there will always be such a sequence.
Do we actually need to state that ear is odd?
Okay, so if you don't state the ear is odd, maybe you want to state something else.
Anyhow, if you add,
Yeah.
because it is a bipartite graph, in one color class that.
Yeah. So if you say that the ear goes from a white vertex to a black vertex, then you don't need to say it is odd. So you have to say one of those two. Yeah, because in general, I could have gone here and I could have added this ear of even length. But then of course you are right, then it is joining two words of the same color. Yeah.
So it's like matching covered subgraphs, right? When you add a
Yes.
even, then it's not matching.
That's another point. Yes. So when you add a path of even length, you will actually not even get a graph on even number of vertices. So it won't be matching covered. No, so I think what Shalu is saying is, you can either say it is of odd length, or you can simply say it joins a white vertex to a black vertex. Both are not necessary. Which is why I have not written both actually. I have written only path of odd length. This implies it will go from white vertex to black vertex because the graph is bipartite.
I think his question is, if you say the sequence is it's a sequence of matching code.
That also implies,
Then
that's right, you're right. So, because I said matching covered, it actually implies that if there is such a sequence, you will be adding a path of odd length. That is also true. Yes. The point here is to define single year. What I mean by single year. It's a path of odd length, but yes, even if you don't define, if this is a theorem, it has to mean this. Yes, good point. Yeah. Okay, good. Yeah, the main point here is, in this course, unlike structural graph theory, whenever we say year, we mean a path of odd length. We shall never allow years to be paths of even length. Even when we go to non-bipartite matching code graphs, we will still stick to adding paths of odd length. Yeah? Yeah. Okay? Good. Any other questions or concerns? So this is one direction. It says that for any bipartite matching code graph, except K2, because I'm starting from cycle, there exists an year decomposition. We'll call this Hetyei's year decomposition. Is that okay? We'll call this kind of year decomposition. Sequence of matching covered subgraphs until here. This we will call So Hetyei's theorem says that a Hetyei's year decomposition exists for every bipartite matching code graph. Okay. Questions, concerns? But now let's go back to two connected graphs. Whitney's year decomposition from STT. Is it one direction or is it both directions? If I give you a sequence like this, in the case of Whitney's year decomposition theorem, does it imply that the graph is two connected? It does. Same thing holds here actually. Hetyei proved both directions. For a bipartite graph, it is matching covered if and only if there exists such a sequence. A bipartite graph, so maybe now I'll state the other direction. So these are the changes. Bipartite graph, I have to exclude on at least two edges. Come on, that should work. I don't want to worry about K1 and all that nonsense. Okay, so bipartite graph on at least two edges. So K2 is excluded and things like K2 and all are also excluded. It is matching covered if and only if H is matching covered if and only if there exists such a sequence. Yeah? This is what Hetyei proved. And this is what you also prove on STT assignment 5. So I will call this QED. And of course that also applies here. Yeah. All right. And we will come back to this point, why we were able to do it from this cycle, this pink cycle, and why we were not able to do it from this pink cycle. We'll come to that point soon. Before that, I want to mention a couple more things about bipartite matching code graphs that are included in the assignment. So let's call this a Hall type characterization. Let's see. For a matchable bipartite graph, H with color classes A and B. The following are equivalent. First one, H is matching covered. This second condition is what we use for calling it Hall type. For every set of white vertices, the neighborhood should be at least one more than its cardinality. The neighborhood of S, cardinality should be at least S plus 1. Of course, this cannot be true for the empty set, and this cannot be true for the whole set. So it is true for every S that is a proper subset of A, and it is not equal to empty. Empty not equal to. Okay. And finally, this is something we discussed yesterday. Matching covered means I can delete two adjacent vertices, white and black, and the remaining graph is a perfect matching. This turns out to be equivalent to deleting any two vertices, white and black. H minus A minus B is matchable for all A in A and B in B. Let me see, is this actually equivalent? If I tell you, yeah, if I put matchable here, then all these three are equivalent. Yeah. Yeah, I don't see a mistake. Sometimes you have to put some more conditions, connected, matchable, then it becomes true. I'm just checking for those corner cases. Right? So this is what you prove. This is also in SGT assignment 5. And then you use this to prove the Hetyei decomposition theorem. Right? And both of these tell you that bipartite matching code graphs are pretty rich. The only thing I want is every set of white vertices, neighborhood should be one more than its own cardinality. Doesn't seem so restrictive. Right? And here, you can just keep adding years and you will get bipartite matching code graphs. So how can it be a restrictive class? It's a pretty rich class. Okay, good. Questions, concerns? Everybody's okay with this? Yeah? So now let's try to answer this point. This point is actually very crucial and it will lead us to a concept that is already covered on assignment 5, but we will hopefully arrive at it more naturally. So it turns out that not only are all these subgraphs going to be matching covered subgraphs, they are going to have one additional beautiful property, okay, which will come for free actually. But when you prove the Hetyei decomposition theorem, you need that property. Okay, so let's think about this. Supposing I add an year. Supposing I have some graph, you don't even need to worry about bipartite right now. You can just think about matching covered graph, or you can just think about adding an year means adding a path of odd length. So the number of vertices I introduce should be an even number of vertices, and the number of edges should be odd number. Supposing this is my graph G, this circle is H here. Let me change it. Supposing this is H, this is G, and this path I added is P. This yellow path. So the vertices of course are already there, but the edges and the internal vertices are new. This is path P. And G is basically H union P. Then I claim that this H has a nice property. It has a nice matching theoretic property. H has a nice property as a subgraph inside G. If I delete the vertices of H, then the remaining graph, it has a perfect matching. Right. we are coming to conformality. So the point here is G minus the vertex set of H is matchable. Yeah?
Brief that thing again.
Right, that's all I'm saying.
So we have a graph.
Yeah, so I have some graph. It is obtained from some graph H by adding a path of odd length, what we call a single year in this course. Right? So I'm going to add a path of odd length. Now I claim that this property holds.
So this H has no additional structure.
No. Right now I'm not assuming any additional structure. Okay. Yeah?
But the vertices in H should be even.
No. For that, I'm not using that also, right? I'm not using that property. Of course, when we apply this, we will assume H has even number of vertices. But to say this statement, I don't need H to have even number or odd number of vertices. Doesn't matter. H could just be 3 vertices like this. This could be H. And still this statement holds.
Yeah, because we don't know the cardinality of vertices in G.
Right. Yeah. I don't know the order of G. Yeah. Good. Yeah. But you agree that whenever I do this, this property holds. The subgraph H, if I delete all its vertices, the remaining graph has a perfect matching. Basically, I'm just using the fact that this is a path of odd length. I'm not using anything about H. I'm just using a property of P. P is a path of odd length. So path of odd length has a perfect matching. Even if you delete the 2 ends of a path of odd length, you still get a path of odd length. So it still has a perfect matching. Yeah, you all agree? This is what we will call conformality. We will say that a subgraph H is conformal if G minus the vertices of H has a perfect matching. Okay? And most of the times when we apply this definition, G will be a matching covered graph. But I'm going to still define it without that, right? A subgraph H of a graph G is conformal if G minus the vertex set of H is matchable. Yeah? Is that okay? That's just the definition. Subgraph is conformal if I delete its vertices, the remaining graph has a perfect matching. It doesn't tell you actually about the subgraph much. It just tells you about G minus the vertex of H. Yeah? Questions, concerns? Is that okay? So now I want you to think about this definition, and now let's go here. Supposing I give you a sequence H0, H1 up to HR. What can you say about HR minus 1? What can you say about the second last graph? Can you say something about this subgraph within the big graph HR, which is equal to H, by the way?
That is also.
Then this is conformal. HR minus 1 is a conformal subgraph of HR. You all agree? HR minus 2 is a conformal subgraph of HR minus 1. Yeah? Everybody with me? Okay. Now let me ask you, is conformality transitive? If H is a conformal subgraph of G and J is a conformal subgraph of H, then is J a conformal subgraph of G?
Write it down.
Okay? Okay, so here is the question. I'll make a drawing actually. So G is a graph, H is a subgraph, and J is another subgraph. This is a good drawing to think of. Now the question is, if H is a conformal subgraph of G and J is a conformal subgraph of H, then what can you say? Can you say that J is a conformal subgraph of G? Yeah? Everybody agrees? Yeah? Okay? So now the question is an observation. Then J is a conformal subgraph of G. Yeah? Yeah? So therefore, all these graphs are going to be conformal in the big graph H by transitivity of conformality. Yeah? Okay, so I'm going to put one more point here. These are all going to be matching covered conformal subgraphs. And that is the reason this cycle did not work. Right? And this is related to Anjali's problem. Right? So the reason this cycle did not work is because this is not a conformal cycle. But if you have an Hetyei decomposition, then we just proved that all the subgraphs are conformal. So you can't have an Hetyei decomposition starting from a non-conformal cycle. That is absurd. Right? The fact that every conformal cycle extends to an Hetyei decomposition, that is also true actually. So there is a stronger version. I will also tell you the stronger versions. Stronger versions are not necessarily proved in SGT. However, you may be proving them in this course. They are not much more difficult. In fact, if I think they are too easy, I will just give it as a DIY, TIY. I won't even put it on the assignments. Right? So in fact, maybe I'll state the stronger version. And the main point here is this pink cycle is not conformal. This is why we were not able to do it. Not a conformal cycle. Whereas this cycle is conformal. Okay. Okay, let's make some space here. So this is the special type of Hetyei decomposition, what we call Hetyei's Hetyei decomposition. Okay, so here is a stronger version that Hetyei proved, or that can be proved basically using the same arguments. Take any bipartite matching covered graph take any matching covered conformal subgraph of G that is not K2, because we are not allowing K2 in your decomposition. This is a technicality. So can G be K2? No, because I need a conformal subgraph that is matching code that is not K2. So therefore G itself cannot be K2. Okay. Then this is similar to the stronger version of Whitney's ear decomposition theorem that is part of SGT and was also covered in Introduction to Graph Theory last semester. So then what you can prove is that there is an ear decomposition, what we call a Hetyei's ear decomposition, such that one of the graphs will be H in that sequence. Another way to think of it is you can start from H and go to G if you don't care about the remaining ear decomposition. Right? Then there exists a Hetyei's ear decomposition. Is it a house or an house? It is a house. A Hetyei's ear decomposition of H that contains, of G that contains H in the sequence. Yeah? I will just put it as a TIY. Actually, it's not difficult. DIY.
Why G is not K2?
Because if G is K2, then the only matching covered conformal subgraph of G would also be K2, which I am not allowing. So because I am not allowing H to be K2, G can't be K2. Technicality. Yeah. And I think the definition of conformal is not written in the best place. Let me write it here also. Okay. All right. Questions or concerns? Let's make some very straightforward observations, which are much weaker than what this theorem is saying. In particular, if you take a bipartite matching covered graph and you keep adding edges to it, edges that join white vertex to black vertex, you will get matching covered graphs. Right? Every bipartite supergraph of a bipartite matching covered graph is also a matching covered. Right? You're just adding trivial ears, single edge ears. Yeah. And essentially that point follows from this point. Delete any two vertices, remaining graph is a perfect matching. So that edge you add will be in a perfect matching. Yeah. Okay. So this already tells you that this is a very rich class, right? Okay. So what else? So that's, let me just check what else I want to mention. Yeah, I did not discuss any operations. We will stop at 5 o'clock today because there is another lecture in this room at 5. So anyways, we can stop that point. Okay, so yeah, so in the remaining time, I want to mention a couple of operations. But before that, let's also discuss one quick corollary of this, which is also mentioned in STT assignment 5. Every bipartite matching covered graph has at least m minus n plus 2 perfect matchings. And this m minus n is related to the number of years. R is equal to m minus n, right? STT. So a quick consequence is that bipartite matching covered graphs have at least m minus n plus 2 perfect matchings. M in general is number of edges, n in general is number of vertices, and all this basically follows from the Hetyei decomposition theorem. If you haven't done it, you can try it, it's easy. The key point is, as you can tell from the formula itself, every time you add an year, you have to show that at least one new perfect matching has been introduced. It gives you a lower bound. Okay, so now we will discuss some operations. Shall we move to that part of the class so that I don't have to erase everything right now? Thank you. So let's think about adding an year, adding a single year as we discussed. Let's look at it in a different way. Adding a single year, it's like adding an edge and then by subdividing that edge. Exactly, subdivide but maintain parity, because we are in matching theory, you always have to maintain parity. So you can subdivide by introducing an even number of vertices. Right? So this operation, yeah, so maybe I'll draw it here. Taking an edge and replacing it by a path of odd length. This is what we will call by subdividing an edge. Yeah, and if you obtain a graph from another graph by repeatedly by subdividing edges, we will call it a by subdivision. The same as saying replace each edge of the original graph by a path of odd length. So you could keep it like that, single edge, or you can make it a path of length 3 or length 5 or whatever you like. For example, here is K33, and now what I can do is I can by subdivide any edges I like. I can by subdivide this edge, I can by subdivide this, by subdivide this. Okay, fine, why not? And this is a by subdivision of K33. Yeah. Okay. So observe that by subdividing an edge preserves the matching covered property, except for one small graph. Always. What is that graph? K2. Right? For K2 you can't do it, and that's because K2 is the only graph. K2 is the only matching covered graph where there exists an edge E such that there is no perfect matching not containing E. This is the main reason. This is also in your STT assignment 5. Right? So your observation is very simple DIY. Every by subdivision of a matching covered graph except silly K2 is also matching covered. So that is perhaps the easiest operation to obtain larger matching covered graphs from smaller ones. But of course that is not very interesting, right? You're just introducing degree 2 vertices. So it doesn't give you matching covered graphs with a large minimum degree, this operation. Okay, so this is one operation. Now we'll discuss one more operation, and this is somewhat closely related to the tight cuts that we discussed yesterday, but it is not exactly the opposite of that. It's yeah, I'll give you, so let's just take an example. I'll just do an abstract example first. Here is a matching covered graph, and here is another matching covered graph. The condition I want is the degree of this vertex is equal to the degree of this vertex. Let's call this G1, this vertex V1, this is G2, this is vertex V2. And the degree of V1 in the graph G1 is equal to the degree of V2 in the graph G2. Right now I'm not even assuming it is matching, I just want to define the operation. Right? To define by subdivision, I did not have to assume the graph is matching covered. Right? So in the same sense, think of G1 and G2 as just two graphs. Think of them as disjoint graphs, right? So their vertices are disjoint sets. Yeah. So now what you can do is you can sort of try to stick these two graphs at these two vertices in some sense. That operation we will call it splicing. So what is a splicing operation? Splicing G1 and G2 is the following operation. Keep the induced subgraph as it is. This is G1 minus V1. Okay? Here I have G2 minus V2. And what I will do is, I will draw these edges like half edges. They don't have another end. I will complete it. So I will just draw these edges like this. These are half edges. Of course, we will not use the term half edges. Please don't use that on assignments. I'm also going to think of these as half edges. What we'll do is, we will, for each half edge on this side, we will basically join it to one of the half edges on the other side. They become a full edge, joining this vertex to this vertex. Right? So, one way to do it is to do it in the very natural way in this drawing. Yeah. So now we have no half edges. Now this edge joins this vertex to this vertex. And of course you can see that there was a choice. I did not have to join it like this. Now let's do a concrete example. For the sake of aesthetics, I will take G1 and G2 to be the same graph. Okay? So I'll take both of them to be this graph. Can someone tell me what is this graph? Wheel, W5, right? In SGT we had Tutte's wheel theorem, so we spent some time on wheels over there. Okay, so now we will take two wheels, two W5s. This is my G1, this is my G2, V1, V2. And we will do two splicings of these two graphs. So the first splicing is the natural splicing. What is natural? Natural means the top edge goes to the top edge, the second edge goes to the second edge, and so on. I get this graph. And now we will do a somewhat unnatural splicing. Although, is it unnatural? We will think about that later. Okay? And now, what I will do is, I will identify the top one with the top one. That one is still the same. I will take the second one and I will go to the third one here. Then I'll take the third one and I'll go to the fifth one here. Then I'll take the fourth one and 5 plus 1, 2. I'll go to the second one. Fourth one will go to the second one. So that will be this. And the fifth one will go to the fourth one. Yeah? What is this graph? If you already know, good for you. If you don't know, think about it.
Going to Petersen.
Good. Prove the isomorphism. See if you can find an isomorphism to Petersen. Well, one thing to note is Petersen graph, if it is the correct answer, this graph should have no cycles of length 4. If you can prove that there are no cycles, or if you can observe that there are no cycles of length 4, then you're actually done, because Petersen graph is the only cubic graph of girth 5. It's on 10 vertices. So, yeah, if you want girth 5 in a cubic graph, length of shortest cycle 5, then you need at least 10 vertices, and equality is attained if and only if the graph is Petersen graph. So if you can find a 4 cycle, then you know that it is not the Petersen graph. And if you can't find a 4 cycle, then chances are that it is the Petersen graph. So can anybody find 4 cycle? If 7 of you cannot find a 4 cycle in 5 minutes, then I think we will conclude it does not have a 4 cycle. No 4 cycle? Okay, if you all agree there is no 4 cycle, then we will conclude that this is the Petersen graph. DIY. Find the isomorphism. Yeah. The point I want to make here is splicing is not a unique operation. This graph is also obtained by splicing G1 and G2. This graph is also obtained by splicing G1 and G2. So there are multiple choices here. First of all, when you say splicing, so the notation we will use is G is obtained from G1 and G2 by splicing. But there are some choices here. What are the choices? I need to tell you what are the vertices where you are splicing. So I will put V1, comma V2, where V1 corresponds to the vertex of G1, V2 corresponds to the vertex of G2. And there is one more choice. What is that choice? Right, here we took the same V1, the same V2, and we got two different graphs. This graph, by the way, is called the pentagonal prism. This is planar and this is not planar. Right? So there are two different graphs for sure. And for example, observe that the pentagonal prism has many 4 cycles. So what is the other variable we should add here? Right? I can't just say splicing G1 and G2 at V1 and V2, that is not enough information. So I need to give you more information. What is that information? How would you capture it? As a function? Right. You can either, the only issue with neighbors, you could have multiple edges. So if your graphs are simple, or in fact more specifically, if V1 and V2 do not have any parallel edges incident at them in G1 and G2 respectively, then you can just take a function from the neighbors. But because we are allowing parallel edges in life, we will take a function from the edges incident at V1 to the edges incident at V2. We will basically want a bijection. We want some bijection that maps these edges to these edges, and we will join according to that bijection, right? So that bijection, I think Lucchesi-Murthy used theta. I will not use theta. I will use maybe sigma or pi or something. Let's go with sigma. Okay. Of course, we will hardly ever use this notation, but I'm just including it for the sake of completeness, right? So when you say you are splicing two graphs, technically you need to make it clear what are the vertices where you are splicing and what is the bijection you are using. This is basically a bijection between partial of V1 in G1 and partial of V2 in G2, right? And the splicing happens according to this bijection. Right? Okay. So this is the splicing notation. Good. But what is the whole point of this discussion? Right? So what do you think is the point of this discussion? We defined an operation. So what are you expecting? Okay, can you make it more precise? Yes, you're right. So splicing should give you matching code graph, assuming something, right? Assuming that G1 and G2 are matching code. Exactly. So that's the key point. This is not difficult to prove at all. Splicing two matching code graphs yields a matching code graph. So that's the second operation. Let me think. Is it always true? Yeah, it is always true. I don't even need to exclude K2. Yeah, okay. Splicing to any two matching covered graphs yields a matching covered graph. Let's do one more example. So this is one of the examples we saw yesterday when we were discussing tight cuts. Okay? This is also a splicing of two matching covered graphs. Yeah? What are the matching covered graphs you are splicing? In that last example, K4 and K33. And observe that in this case, I can just write the notation K33 spliced with K4 or the other way around. In this example, I don't need to give you any more information. Do you all see that? No matter how you do the splicing, which vertex V1, V2 you choose, what permutation you choose, you will get the same graph. And the reason for that is because both of these are very symmetric graphs. Right? They are both vertex transitive graphs. And I think that is not enough information here, but one of the graphs is actually K4. That makes it even more specific. Right? So here I can just tell you K33 splice K4, and up to isomorphism the graph is basically defined uniquely. So when this happens, we will drop some of the notation, right? We will not write V1, V2 pi because it is unnecessary. You will get the same graph no matter what you do. Yeah? Okay. But there is one more point I want to discuss. When you splice two matching covered graphs, or for that matter, when you splice two graphs, you get a natural cut in the resulting graph, right? This cut. So if I splice two graphs G1 and G2, I get the graph G. This is my final graph G. Then the corresponding cut, we can call it the splicing cut. Right? So for any splicing operation, the resulting graph will have a natural cut, and that we will call the splicing cut. Is that okay? This is just a term for splicing. This has nothing to do with matching covered. Okay. So now let's look at matching covered examples. I splice these two matching covered graphs. Observe that these two are matching covered. That is not difficult to see. Wheels are matching covered on even number of vertices. So I splice these two. As per this observation, I get a matching covered graph. I could get this graph, I could get this graph, or some other graph depending on the bijection, right? Now these splicing cuts in these matching covered graphs have the property that the two contractions are matching covered. Right? For each cut, you can define the two contractions, shrink x into single vertex or shrink x bar into single vertex. So naturally, because I obtained this matching covered graph by splicing two matching covered graphs, this splicing cut has a property that the two contractions are matching covered. Such cuts, we will call them separating cuts. I'll write down the definition. A separating cut of a matching covered graph is any cut partial of x such that both partial x contractions are also matching covered, right? And the observation I want to make, which is a trivial observation because of the way we define things, the corresponding splicing cut is a separating cut, right? Splicing any two matching covered graphs, G1 and G2, yields a matching covered graph, G, and the corresponding splicing cut in G is a separating cut of G. Naturally, because the two contractions, what are the two contractions? They are G1 and G2. They were matching covered. So, what I am saying here is a triviality. But it's a crucial triviality. Okay? So, whenever you splice, you will get a matching covered graph that has a separating cut naturally. Whenever you splice two matching covered graphs, the resulting matching covered graph will have a separating cut. Right? Okay. This separating cut may or may not be a tight cut. In this example, it is tight. In these two examples, you can check that they are not tight cuts. Tight cuts, so one of the following statements is true. Separating cuts are special types of tight cuts. Second statement, tight cuts are special types of separating cuts. Which of them is true? Every separating cut is tight. Second statement, every tight cut is a separating cut. Every tight cut is a separating cut. Yeah? Converse is not true. Exactly. Every tight cut is a separating cut. This follows from yesterday's DIY. For any tight cut, you have to prove that the two contractions are matching covered. Therefore, it is a separating cut. Right? However, the converse is not true, and these are examples where you can see that. These are separating cuts, but not tight. Yeah? Okay? Questions, concerns? So I want to give you a TIY. What is the definition of tight cut? Let's recall. Can someone recall for me? Okay.
If I take any perfect match,
Mhm.
the intersection with the cut is going to be equal to 1.
Right. For every perfect matching. Is that true? Everybody agrees? Okay. So tight cut is a cut. It is any cut C such that M intersection C is equal to 1 for every perfect matching M of the graph. Yeah. What I want to do is I want you all to come up with a similar definition, also known as characterization, for separating cuts. It should be some statement about perfect matchings, but it is not going to be as straightforward. It is going to be more complicated. Okay? So, characterize separating cuts in matching covered graphs. Something like this. A cut C of a matching covered graph G is a separating cut if and only if something. I'm thinking how much of the something should I already give you? So this is a statement about the set of perfect matchings of the graph. For every perfect matching, intersection is equal to 1. That is what it is saying. I want you to think of a similar statement here. Some statement regarding the set of perfect matchings of the graph G. But it is going to be much more complex than this. Okay? Here you have a universal quantifier. For every perfect matching, M intersection C is equal to 1. Here you are going to have perhaps two quantifiers. Okay, it is not going to be a single universal quantifier. It might be more complicated than that. But anyways, I'll let you think about it. Okay, it's not too difficult. You just have to pay attention to the original definition of separating cut. You want the two smaller graphs to be matching covered. So when does that happen? Okay, so this is our TIY. Okay, and let me see if there's anything else I want to really cover today. So what we have seen is yeah, I think I want to just cover this much today. One thing I want to mention is I mentioned hypomatchable graphs. We saw that for a maximal barrier, all the odd components will be hypomatchable. So I was looking at Lucchesi-Murthy. They use the word critical instead of hypomatchable because they use bicritical for deleting two vertices. So historically, factor critical was used for these graphs. Generally in graph theory these days, when you say critical, many people think of chromatic graph theory. There is a definition of critical graphs in chromatic graph theory related to colorings, which is why many people avoid using critical for factor critical and hypomatchable. But in the Lucchesi-Murthy book, they are using critical because anyways they are not talking about chromatic number, right? So they decided to use critical. So anyways, these three terms are used for the same thing, right? Yeah. So my plan is to next go to tight cuts. What we have done till today, we have essentially completed almost everything that appears in chapters 2 and 3 of Lucchesi-Murthy. Whatever things I have skipped, they are very straightforward things. Some of them may appear on your assignments. Yeah, and you can also just flip through the book and go through it yourself. You all have a copy of the book, so feel free to just go through it. We are basically done with chapters 2 and 3, and next we will go on to tight cuts. So today is Thursday, so we won't meet, we will directly meet on Monday. Monday is not a holiday, right? Good. So we'll meet on Monday, and my plan is to give you an overview of what we will be covering in the tight cut decomposition theory. And once we do that overview, then we will jump into specific proofs. The first non-trivial proof we have seen is the canonical partition theorem. Everything else was basically straightforward stuff. A lot of terminology, but nothing really difficult. But next difficult results will be related to tight cuts. That's the plan for the next couple of weeks. Yeah, and I'm planning to follow Lucchesi-Murthy as much as possible because that also gives me a way to sort of figure out the narrative, especially because this is the first major offering of this course. All other offerings have been sort of mini offerings. So it will also help me to follow a book rather than coming up with the narrative every time, and I can focus on the proofs and the details. And in future offerings, I may customize more according to my style. But this time I'm trying to follow the book as much as possible. Yeah. Okay, thank you, and have a nice weekend. I'll see you on Monday.